So last week we talked about one proportion and then two proportions, and this week we talked about one mean. And so today, logically, we're going to talk about two means. So we're going to be looking at inference for the difference in two means, two population means. And this beginning part, don't write down any of these formulas. Wait till we get to the actual hypothesis test and confidence interval. This is just going to walk us through the thought process of where those formulas come from. But just like with everything else that we've been looking at, then we're going to use a theoretical distribution as a model to help us come up with our p-values and our confidence interval values. And so the standard error when we're looking at the difference in two sample means is this formula here. So we're going to have square root of sigma 1 squared over n1 plus square root, or sorry, I'm saying it all wrong. We're going to have the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now, you notice that we have sigmas in this formula. And when we know what sigma 1 and sigma 2 are, then the difference in those two sample means, the distribution, the sampling distribution for the difference in those two sample means can be approximated by a normal distribution. But of course, in real life, we typically do not have the values of sigma 1 and sigma 2, our population standard deviations. So instead, we're going to approximate those by using S1 and S2. And just like when we talked about one mean, how if we use S to replace sigma, then that changes the resulting distribution a little bit. And instead of being a normal distribution, it becomes a t distribution, which is a little bit flatter and a little bit more spread out. And that same thing is going to happen here. So when we replace sigma 1 and sigma 2 with S1 and S2, changes everything so that now the sampling distribution for x bar 1 minus x bar 2 is going to be an approximate t distribution. And this is going to be based on the conditions that either both populations are normally distributed or both sample sizes are large. Now, one different thing from when we were talking about one mean is that the resulting distribution that we're looking at is an approximate t distribution, not an exact t distribution like it was when we looked at one mean. And because it's an approximate t distribution, then the way that we calculate degrees of freedom is a little bit interesting. And in fact, kind of in practice, there's kind of two different ways that people find the degrees of freedom for this approximate t distribution. And so I thought, hey, as a class, why don't we just go ahead and look at both of these options, and then we can decide as a class which one we like, and then we'll just use that one. That way we're all on the same page doing the same thing. Sound like a plan? Okay, so this first option, like how many of you are one of those kind of people that you like things to be exact, like everything has its place, you like order, you like to, have like the exact kind of things, you're going to like this first option. So this first option, we can just use this little formula right here to calculate our degrees of freedom. All we have to know is S1 and S2 and N1 and N2. We can just plug it in all over and we'll get this great thing here. So that's option number one. Okay, so and I really like exact things. I guess that's probably why I'm a math person. I like it when 2 + 2 always equals 4. It's kind of great. Unlike English, where sometimes 2 + 2, the teacher doesn't like it. All right, so here's option number 2. This one's going to be less exact. You're typically going to get a smaller number of degrees of freedom this way, but we could just use the smaller of N1 minus 1 and N2 minus 1. All right, so those are our two choices, okay? We can use fun formula or just take the smaller of N1 minus 1 and N2 minus 1. What do you guys think? Option 1, option 2? Kind of like going to the eye doctor, right? 1 or 2? 1 or 2? 2. Everybody's voting for option number 2? Come on, there has to be somebody out there that really loves formulas and exactness. Nope. All right. Oh, yay, Anissa, she's going for option number 1. I think we're outvoted. So we're going to have to go with option number 2, which is we're just going to take the smaller of n1 minus 1 and n2 minus 1. And you might even wonder, like, why did I even bring up that other nasty formula? Because never in the history of ever has any class actually chosen option number 1. And even me, who thinks a lot of weird things are fun, doesn't really think this looks that fun. I mean, look at all those like squares, like we're squaring and then we're squaring again, and all kinds of, you know, craziness here. So the reason why I even bring this up is because we wouldn't think this is very fun to calculate by hand, but a computer has a very warped version of what is fun and can easily calculate degrees of freedom this way. So if you are looking at a computer output or something like that, then you might see the degrees of freedom calculated using this method. And it's going to be different than what you get when we do this method here, option number 2. So I don't want you to panic. And I'm going to show you even in the applet that we're going to use today, then it's going to use this formula to figure out the degrees of freedom rather than this one. So when you see that, I don't want you to be like, oh my gosh, I calculated degrees of freedom wrong. No, you didn't do anything wrong. It's just that they used option 1 and you opted for option number 2. Okay, so let's talk about how we're actually going to use this stuff now, starting with a hypothesis test. So first of all, for our hypothesis test, then we're going to write our hypotheses. Null hypothesis is always that mu1 is equal to mu2. And then the alternative hypothesis is going to be that mu1 is either greater than, less than, or not equal to mu2. So just like we wrote hypotheses for 2 means before, nothing's different there. Our test statistic is following the same basic format. We're going to have statistic minus null over the standard error. So our sample statistic is this x bar 1 minus x bar 2. When we think about the value under the null hypothesis, if I look at my null hypothesis, if mu1 is equal to mu2, then mu1 minus mu2 would be equal to 0, right? So if mu1 equals mu2, then mu1 minus mu2 equals 0. So the value in the null hypothesis in this case is just 0. So sometimes you might see it written like this with parentheses here and then minus 0. But of course, mathematically, subtracting 0 doesn't change anything. So oftentimes we just leave that part out because it doesn't make a difference in the actual calculation of the formula. But if you're strictly sticking with statistic minus null over standard error, then that's what it would look like. All right, so the numerator is our sample statistic, x bar 1 minus x bar 2, and the denominator, this whole denominator part, and all these formulas, these are the ones you're writing on your notes pages, if you didn't figure that out already. This whole denominator is our standard error. And just like we had with 2 proportions, we can use that standard error calculator for 2 means as well. So we can get it to calculate all this whole value in the denominator here. All right, now there's the conditions for doing this are, first of all, we need to have 2 simple random samples. Actually, I'm going to say 2 independent simple random samples. So 2 independent simple random samples. And then the second thing is that we need either both populations to be normal or both sample sizes to be large. So either both populations are normal or both sample sizes are large. So I'll say both N1 and N2 are large. All right, and remember, we're going to check this when we can look at the sample sizes. That'll help us check it. And also, if we have the data, we can do histogram dot plot of the data, and we can check to see if the data is roughly symmetric with no extreme outliers. So I'm going to say check by looking at histogram or dot plot of the individual groups. Okay, so I'll say of each sample. And if I'm running out of room here, if roughly symmetric with no extreme outliers, then we're good. Then we meet that condition. All right, and over here somewhere by your test statistic, we should put in that the degrees of freedom are going to be the smaller of n1 minus 1 and n2 minus 1. All right, so we know how to write the hypotheses, we know how to compute our test statistic, we know our degrees of freedom, and now we know the conditions, which is 2 independent simple random samples, and then either both populations need to be normal, and by that we mean if we look at the sample data and it's roughly symmetric with no extreme outliers, we're good, or the sample sizes can be large. Only one of those two things has to be true in order for us to meet the conditions. If both of them are true, then it's a bonus, but as long as one of them is true, then we're happy. All right, so let's look at how we would do this in an actual example. So we want to know which brand of breakfast cereal has the most sugar. A group of statistics students decided to find out. They took a simple random sample of 15 Kellogg's cereals and separately a simple random sample of 30 General Mills cereals and measured the sugar content per 30 grams of cereal. So we want to know, does Kellogg's or General Mills have more sugar on average? So first thing we're going to do is define our parameters. So we're looking at two means now. So we have two parameters. We're going to have mu1 and mu2, or we could call them mu-k for Kellogg's and mu-g for General Mills, whatever you want to do it. So I'm going to say mu-k and mu-g. So mu-k would be the mean sugar in Kellogg's cereals. And technically, it's the mean amount of sugar in 30 grams of a Kellogg's cereal, but as long as it's detailed enough that it makes sense, it's all good. And then mu-g would be the mean sugar in General Mills cereal. All right, so now we've defined our parameters. We're ready to write our hypotheses. So our hypotheses are always written about the population parameters. So null hypothesis is that the two means are equal. So mu-k equals mu-g. And then my alternative hypothesis is going to look very similar. The only difference is the symbol that I'm going to use. So I have to decide between greater than, less than, or not equal to. And if I look back at my research question here, does Kellogg's or General Mills have more sugar on average? What symbol do you think I should use? Should I use greater than, less than, or not equal to? So looking at my research question, I wanted to know do Kellogg's or General Mills have more sugar? So in that case, we weren't really sure which way it was going to go. We thought it could be Kellogg's or it could be General Mills that had more. So we're going to use not equal in the alternative hypothesis. So null hypothesis, mu-k equals mu-g, alternative mu-k not equal to mu-g. All right, next we're going to compute the sample statistic. And the notation for the sample statistic here is going to be x bar k minus x bar g. Okay, so I need to know the mean for Kellogg's and the mean for General Mills. So I took this data and I put it into stat key and had it in the, if you put it in the descriptive statistics part, some of you may have forgotten how to do this, but back in chapter 2, when we originally talked about means and standard deviations and histograms and all that fun stuff, remember how we could just go into stat key and we could either import the data, or we could click on edit data and type the data in ourselves in there. You might have to do this in some of your Wiley Plus homework, which is another reason why I'm bringing this up. But basically, once you do that, in this case, we would go to one categorical, one quantitative variable. That's where I would get it when I'm looking at two means here. And it'll calculate the descriptive statistics for me with all this stuff. So first of all, I need the means here. So the mean for Kellogg's was 9.328. The mean for General Mills, 6.834. So X bar K minus X bar G is going to be 9.328 minus 6.834, which is 2.494. All right, so this part here, the 2.494, this is my sample statistic. And the X bar K minus X bar G, this is the correct notation for the sample statistic. All right, so now I define my parameters, I've written my hypotheses, I've got my sample statistic all ready to go. I'm getting excited about doing the hypothesis test, but first I need to check my conditions. So remember, to check the conditions, I can do histograms or dot plots of the data. I can also evaluate the sample sizes. So I need either both populations to be reasonably symmetric with no extreme outliers, or I need both sample sizes to be 30 or more. So in this case, for Kellogg's, if you remember for Kellogg's, N was equal to 15. So that is not 30 or more. So I would need to look at a histogram here and verify that it looks roughly symmetric with no extreme outliers. And if I look at this one here, look at that. This is pretty lovely. Okay, it looks pretty symmetric. I don't see any extreme outliers. This also gave me a box plot on the side here. And based on my box plot, I can also see that it's fairly symmetric. I don't have any extreme outliers there. So Kellogg's looks pretty good. For General Mills, N was equal to 30. So I actually already meet this condition because my sample size was large for General Mills, but I could also look at the histogram for General Mills. This one's not quite as bell-shapey looking, but it is fairly symmetric and I don't see any extreme outliers either. And definitely looking at my box plot, it looks pretty good there too. So I would meet the conditions here. So overall, I meet the conditions because for Kellogg's, no extreme outliers, reasonably symmetric. And for General Mills, same thing. Also, my sample size is 30 for General Mills, so we're good. All right, now that I've done all of that, then I'm finally ready to compute my test statistic, find my p-value, and draw conclusions. So my test statistic formula is this one, x bar 1 minus x bar 2 divided by this thing. Now remember, this whole thing down here is my standard error. So I can use that standard error calculator, that kind of standard error applet, whichever one you want to call it, to compute this whole denominator for me. So I'm going to do that. I'll put SE up here and we'll go see if we can find it. Now, in order to use that standard error calculator, I do need to know what S1, N1, S2, and N2 are. So remember, this was all back in that, there it goes, in this table here. I have my standard deviations, 2.176 and 2.642. And I also have my sample sizes of 30 and 15 here. So I would write those down. I wrote those down over here on my paper. I think you guys have it on the printout if you printed out my notes pages. And then I'm going to come over and find that standard error calculator. So remember, there's a couple places you can find the standard error calculator inside of Blackboard. If you go to course links, then you can scroll down and there's standard error calculator right there. I've also tried to put it in the weekly folders under helpful resources. So you can click on that and then you can get the standard error calculator that way. Once in the standard error calculator, this time we're looking at two means. So the one that we want is this one right here, SE for the difference of sample means from independent samples, since that's what we're working on. So we go ahead and click on that one. And all we have to put in is our standard deviation and our sample size for each group. So starting with Kellogg's, for Kellogg's, the standard deviation was 2.642. And the sample size was 15. For General Mills, the standard deviation was 2.176, and the sample size was 30. All right, so I'm going to hit compute standard error. Notice something that's different when we're working with means versus proportions. When we were doing it for proportions, we had to check saying we were doing a hypothesis test or a confidence interval because the standard error was different when working with two proportions, depending on if we were doing a hypothesis test or a confidence interval. And here, now that we're dealing with means, two means, there's no difference. It's the same standard error for the hypothesis test as it is for the confidence interval. So that's that makes some things a little bit simpler. So I hit compute standard error, tells me my standard error is 0.7894. So this is the number I'm going to use in the denominator of my test statistic. And also you can see down here that they tell you the precise degrees of freedom is 23.79. So the precise degrees of freedom is what you get when you use that funky formula that we saw. So when we find the degrees of freedom, we're not going to get 23.79. We're going to get something smaller than that. But that's where this number came from. In Wiley, or in your textbook in general, if it refers to the precise degrees of freedom, it's talking about the funky formula. If it's talking about the conservative degrees of freedom, that's talking about the way that we planned on doing it, using the smaller of n1 minus 1 and n2 minus 1. So anytime they talk about conservative degrees of freedom, that's just the regular way that we find that we're going to find the degrees of freedom in our class. Okay, so going back to my calculations here. So my standard error, this is the one I just got from the applet, 0.7894. And so now I can plug these in here. So I have x bar 1 minus x bar 2. So we just calculated that on a previous slide. It was 2.494. But just so you remember where those numbers came from, I'm going to write out the x bar 1 and x bar 2 again. So I get 9.328 minus 6.834 divided by the standard error, which is 0.7894. Okay, notice that this 0.7894, it's after this has been square rooted and everything. So once you get this standard error number, you don't have to do anything extra to it. You just throw it in the denominator. All right, so now I'm going to take that 2.494, which is what I get in the numerator, divided by 0.7894, and I got 3.159. So this 3.159, this is my test statistic. All right, and I'm going to use my test statistic to help me find my p-value. And I'm going to do that using stat key. But in order to find the p-value, I need three things. I need to know my test statistic, I need to know my degrees of freedom, and I need to know what type of alternative that I had. So here's my test statistic. Next, let's look at degrees of freedom. So degrees of freedom is going to be the smaller of n1 minus 1 and n2 minus 1. So in this case, that's going to be the smaller of 15 minus 1 and 30 minus 1. So that's 14 versus 29. 14 is smaller than 29. So we end up with 14 degrees of freedom. So you can see that this is a smaller number than the precise degrees of freedom that we would have gotten using the funky formula. All right, so now I have my test statistic, I have my degrees of freedom, and maybe I just need to remind myself what my alternative what my alternative hypothesis was. It was not equal, so I'm going to do a two-sided test. All right, so I'll just write over there, HA was not equals. Okay, so those are the three things I need in stat key in order to find p-value: test statistic, degrees of freedom, and type of alternative. So now I'm going to head over to stat key. Okay, in stat key, we're still using the theoretical t distribution. Anytime we're dealing with means, we're going to use the t distribution. When we're dealing with proportions, we're going to use the normal distribution. So I'm going to click on T here. And remember, we just found that we had 14 degrees of freedom. So I'm going to enter in that 14 degrees of freedom. And Here, actually, I'm going to write down all the three things that we needed to know. I'll just write them on the side here so that we remember. So we had 14 degrees of freedom. Our test statistic was equal to 3.159, and our alternative hypothesis was not equal to. Okay, so because my alternative hypothesis is not equal, then I'm going to click on two-tail here. And once I click on two-tail, then I put my test statistic in the bottom. If I have a positive test statistic, it goes on the right side. Negative test statistic, it goes on the left side. So 3.159 is positive, so I'm going to put that over here, 3.159. All right, and then to find my p-value, because it's a two-sided test, I have to double this floating box, or essentially add those two floating boxes together. So again, I'm going to label a few things here. So down here, this is my test statistic. And then this one here is my tail proportion. So to find my p-value, I'm going to have to take 2 times that tail proportion. So 2 times 0.0035, which is going to be 0.007. So my p-value ends up being 0.007. Now we finally found our p-value. We're ready to go ahead and start drawing some conclusions. So I'll come back here. We found the p-value. Our p-value, again, was 2 times 0.0035, which is 0.007. So our conclusion, well, 0.007 is really, really, really low. And when p is low, then HO must go. So we're going to reject the null hypothesis. We have sufficient evidence that Kellogg's cereal has more sugar per 30 gram serving than General Mills cereal. The Pygmalion effect is this idea that the greater the expectation placed upon people, the better they perform. So they did this study where they told teachers that certain children were expected to be growth spurters. And they told the teachers that these children were selected based on this Harvard test of inflected acquisition. But in reality, there is no such test. And the children that they told the teachers about were just randomly selected from the class. So really these kids were just a random sample from the class. They weren't really any different than anybody else in the class. But the teachers were told that these kids were growth spurters. And then after a year of being with these teachers, they measured the change in IQ for all the kids. And they wanted to find out if the kids that had been labeled growth spurters actually did better than the kids who were not labeled anything. And so this was their sample data from that. And we wanted to know if this provides evidence that the Pygmalion effect actually exists, that merely expecting a child to do better actually causes the child to do better. So rather than going through this all together, I'm going to break you guys into breakout rooms and let you work through this with just a couple other people in the class, and then we'll come back together and go over the answers and make sure that we're all on the same page. All right, so let's look at what we got here. So for the hypotheses, mu1 equals mu2, alternative mu1 greater than mu2, and mu1 was the average change in IQ for the growth spurters, mu2 the average change in IQ for the control group. And if you labeled yours like mu-G and mu-C or something like that, that's great. For our sample statistic, then we're going to have 12.22 minus the 8.42, so we get 3.8. Checking the conditions, we didn't have the actual data, so we couldn't do a graph here, but looking at both of our sample sizes, they're both greater than or equal to 30, so we do meet the conditions that way. For our standard error, you could plug the numbers into this fun formula, or you could go over and use the standard error calculator. If you do that, either way, actually, then you get 1.8128 for the standard error. And so when you're computing your test statistic, you're going to have it's basically the sample statistic divided by the standard error for this problem. So you're going to get 3.8 divided by the 1.8128, which gives you 2.096. So this is your test statistic. For the p-value, you're going to have the smaller of 65 minus 1 and 255 minus 1 for your degrees of freedom. So that's going to end up being 64, and it's a greater than test. And we need our test statistic, the 2.096. So if you do all that, you end up with a p-value of 0.02. So if we use our standard alpha equals 0.05 for our significance level, then we would reject the null hypothesis and conclude that we have evidence that positive teacher expectations significantly increase IQ scores on average. Or you could say something like our standard, we reject the null hypothesis, we have the sufficient evidence that the mean IQ change for growth spurters is greater than the mean IQ change for the control group. All right, so let's talk about confidence intervals now. We talked about hypothesis testing, and let's talk about confidence intervals. So in general, the formula for a confidence interval is going to be our statistic plus or minus our margin of error, which we've defined as Z star times the standard error. And when we replace sigma with S, then instead of using Z star, we're going to use T star, just like we did in section 6.2. So what that ends up looking like for our confidence interval is this. Okay, so we end up with X bar 1 minus X bar 2 plus and minus T star times this whole square root thing. And remember that this whole square root thing, including the square root itself, is our standard error. So if you use the standard error calculator to find standard error, you just replace that whole thing with the value that you get from the standard error calculator. And the conditions are the same as they were for the hypothesis test. So we need the 2 independent simple random samples, and then we want both populations to be normally distributed or both sample sizes to be large. So same exact conditions as the hypothesis test. And we would check them the same way by doing a histogram or a dot plot to check for normality or to check to see if they're reasonably symmetric with no extreme outliers. And then we would look at the sample sizes. And degrees of freedom are also exactly the same. So it's going to be the smaller of N1 minus 1 and N2 minus 1. So let's look at an example here. We're going to look back at the sugar in breakfast cereals example. We found out previously that there was a significant difference in Kellogg's and General Mills cereal in the amount of sugar. And we found that Kellogg's had more sugar than General Mills. That's what we found out from our hypothesis test. So now we want to find out how much more sugar does Kellogg's have than General Mills. So to answer that question, we would construct a confidence interval. So we're going to look at a 95% confidence interval. So first, we're going to define our parameters. So we're going to have 2 parameters, same 2 parameters that we had before. So mu1 would be the mean grams of sugar in Kellogg's, and mu2 would be the mean grams of sugar in General Mills. Or you could call them mu k and mu g if you feel like that's more informative. Next, we're going to compute our sample statistic. Again, we did this previously, but we'll go ahead and show it again here. So our sample statistic when we're looking at 2 means is X bar 1 minus X bar 2. So in this case, X bar 1 minus X bar 2 is going to be the 9.328 minus the 6.834, which gives us 2.494. So our sample statistic is the 2.494, and the correct notation for that sample statistic is going to be, the X bar 1 minus X bar 2 over here. Next, we would check our conditions. Now, since we already checked the conditions to do the hypothesis test, then we know that we already meet the conditions. We looked at those histograms. Both of them were fairly symmetric with no extreme outliers. So we did meet the conditions to use the t-distribution. All right, now we're ready to construct our confidence interval. So our confidence interval has multiple parts. We have our sample statistic plus and minus t star times our standard error. So let's go ahead and find some of these values before we get started here. So remember, this whole thing, including the square root sign, is our standard error. And the standard error we can get by using that standard error calculator. And in fact, we did do this earlier. So when we did the hypothesis test earlier, we found out that the standard error was equal to 0.7894. So I'm just writing that down from my notes that we did the first time. It should already be in your notes. Now, the next thing that we need to figure out is T star. To find T star, we need to know two things. We need to know our degrees of freedom, and we need to know our level of confidence. So our degrees of freedom are the smaller of n1 minus 1 and n2 minus 1. So if I back up here, we can see that General Mills had a sample size of 30, Kellogg's had a sample size of 15. The smaller of 30 minus 1 and 14 minus 1 would be 14. So my degrees of freedom is 14. And my confidence level was 95% that it asked for earlier. All right, so as long as I know degrees of freedom and my confidence level, then I can find my T star. So there's two ways we can find T star. You can find it using the table, or you can find it using StatKey. So first I'll show you how to find it using StatKey. In StatKey, we would come to theoretical distributions and choose the T distribution. I'm going to enter in 14 for my degrees of freedom. Then I'm going to click on two-tail and make sure that that center box has my level of confidence in it. In this case, my level of confidence was 95%, and that's the default number that comes up, so I don't really have to change anything. If I do that, this bottom number down here is my T star value. So my T star would be 2.145. Now let's look and see how we would find this using the table. Remember, you are going to be allowed to have a printout of that table on the exam if you would like. You're allowed to print that out ahead of time. So if I look under the resources folder, I'm looking for the critical values for confidence intervals form here. And for T star, it's this big long part of the table. I'm looking at my level of confidence and my number of degrees of freedom. So I had 14 degrees of freedom and a 95% confidence. So you can see that that gives me a T star of 2.145. So same exact thing that I got from StatKey. As long as your degrees of freedom are smallish, under 30, then you're going to get the exact same number from StatKey. For degrees of freedom between 30 and 100, you're going to get pretty close, probably close enough to be just fine. If you have more than 100 degrees of freedom, then you're welcome to use the table on your written homework and for the exam. But for your Wiley Plus homework, you're probably going to want to use StatKey to get your T star values, because these values over here are they're basically just saying use the normal distribution values, and you're going to have answers that are just off enough that Wiley Plus might get mad at you. So I recommend using StatKey to get your T star if you have a larger sample size, especially if you have one over 100 and maybe even over 30, you should probably use StatKey. Back to my problem here then, I'm going to write down my T star. T star was 2.145. So now I have all the pieces that I need in order to do this problem. So looking here, my sample statistic, remember we calculated this on this earlier slide. So the difference between X bar 1 and X bar 2 was 2.494. So I'm going to say 2.494 plus and minus my T star of 2.145 times my standard error of 0.7894. I'm going to multiply those together. And if I multiply 2.145 times 0.7894, then I get 1.693. So this 1.693, this is my margin of error. So I'm going to add and subtract that margin of error from my sample statistic. So I'm going to take 2.494 minus 1.693, which gives me 0.801. And then I'm going to take 2.494 plus 1.693, which gives me 4.187. So this is my confidence interval, and my last step is going to be to interpret this confidence interval. So to state my conclusion then, I'm going to say we are 95% confident that Kellogg's has between 0.801 and 4.187 more grams of sugar than General Mills on average. And in parentheses, I'm going to put per 30-gram serving so we can be technical here. So we're 95% confident that Kellogg's has between 0.801 and 4.187 more grams of sugar than General Mills per 30-gram serving on average. Next example is about video games and GPA. There's 210 first-year college students that were randomly assigned to a roommate, and 78 of those that were randomly assigned ended up with a roommate who brought a video game to college. And of those, their average GPA after the first semester was 2.84 with standard deviation 0.669. And then there was 132 students that were assigned to roommates who did not bring a video game to college, and their average GPA after the first semester was 3.105 with a standard deviation of 0.625. So we want to know, how much does getting assigned a roommate who brings a video game to college affect your first semester GPA? So we want to do a confidence interval on the difference in the mean GPAs for college students that get a video game roommate versus college students who did not get a video game roommate. So I'm going to put you back in your breakout rooms again for about another 9 or 10 minutes so you can collaborate with them and see if you can come up with the confidence interval for this one, and then we'll get back together and talk about it. All right, welcome back everybody, and let's go ahead and look at the answers and see how they compared to what you got. So we're finding a 90% confidence interval here. So first part, we're going to define the parameters. So I called mu1 my mean GPA for students with video game roommate, and mu2 the mean GPA for students without a video game roommate. If you called yours the reverse, it's not a problem. It just means that all of your numbers are going to end up having the opposite sign of mine. And that's totally fine because we're estimating the difference. Okay, and the difference is going to be the same either way. The sign on it just indicates the direction of, either the video game roommates had this much less GPA, or the without video game roommates had this much more GPA kind of thing. So for our statistic, our sample statistic, we're just subtracting those sample means, 2.84 minus 3.105. So I get negative 0.265. Checking the conditions, all we had to go off was the sample width was the sample sizes here, and both of our sample sizes were greater than or equal to 30. So we do meet the conditions there. Next, we're going to find T star. So in order to find T star, we need to know two things. We need to know our degrees of freedom, and we need to know what level of confidence we want. So in our case, for degrees of freedom, we're going to take the smaller of 78 minus 1 and 132 minus 1. So the smaller of those is going to be 77. So we have 77 degrees of freedom. And we had 90% confident. So if you use stat key, you end up with a T star of 1.665. I think if you use the table, it's really close. I think you might get 1.669 from the table. I can't remember the exact number from the table. If you use the table, it's just fine. Oh, 1.671 is what you get from the table. Which is fine. So then finding the standard error, you can calculate it using the fun formula, or you could use the standard error calculator. So when I did that, then I got 0.09326, 0.09326. So computing our confidence interval, then we would take our sample statistic plus and minus T star times that standard error. So I get negative 0.42 to negative 0.11. So interpreting that in context, we're 90% confident that getting assigned a roommate who brings a video game to college decreases the mean first semester GPA between 0.11 to 0.42 points. So again, if you flip-flopped your mu1 and mu2, you would have gotten positive numbers here, and that just meant that without the video game roommate, those people did that much better. And then this is saying with the video game roommate, this is how much worse that you did. So try not to get a video game roommate, I guess, is the moral of this story. All right. So how did everybody do? Did you get pretty close? Thumbs up, thumbs down? Lots of thumbs up. Excellent. All right. So that is the end of today. So have a super fantastic weekend. And then we just have one more section in chapter 6 that we're going to cover next Tuesday. And it's even kind of like a pretend section. Not pretend, but when we get to it, we're going to find out that really we already know how to do the stuff in section 6.5 because we've already done it before. So this is just kind of a new take on a method that we've already used before. So it's not going to be that hard. So today, once you get through today, we're done with the hardest stuff for chapter 6. 6.5 will be kind of on the downhill slope, and then you'll be all ready to take another exam.